Hello, statistics students. In previous lessons, we've talked about what we're looking for when we are analyzing a distribution. As I've mentioned before, our brains are not really designed to handle large quantities of numbers, so we like to graph things and see what does the picture tell us. And when we describe the distribution, when we describe the picture, we look at shape, center, and spread. We've already discussed shape and center in previous videos. Today we're going to talk about spread, which is, missing the word here, it's defined by our measures of variation. Before I do that though, I do want to remind you of this information, all the different symbols that we use. And you'll notice again that these population variables are all Greek letters. This is a lowercase mu, an uppercase nu, a lowercase sigma squared, and a lowercase sigma. These sample variables are Roman letters, x bar, lowercase n, lowercase s squared, and lowercase s. Some measures of variation, well, the range of the data. Take your maximum value minus your minimum data. That tells you how spread out your data set is, how much it's varying. And we can also look at the interquartile range, which is how spread out is the middle 50% of our data. The key measures of variation that we're going to focus on today, however, are variance and the standard deviation. Now, I'm just going to say right now that all the cool kids call this the standard dev. Do you want to be one of the cool kids, or do you want to call it the standard deviation? I guess we'll find out. There are two formulas for variance. And because of that, some students make the mistake, they figure that there are two different variances for a data set. This is not true. There are two different formulas for calculating variance depending on whether your variance is whether you're measuring the variance of the entire population or if you're just measuring the variance of a sample. So there's any given data set only has one variance. But if I give you a data set and say, find the variance of this data set, the first thing you have to do is say, is this a population data set or a sample data set? Without that information, you cannot calculate the variance. So let's focus on the population variance for a minute. I define variance as an average of the squared distances from the mean. So the first thing we do, now it's silly to take a variance of a data set that has only 3 points in it, but let's do it just for explanatory purposes. Here's my data set, 1, 4, and 7. These are my x sub i's. This is x sub 1, x sub 2, and x sub 3. The average, if you add these up and divide by 3, you get 4. So I need to find the distances from the mean. So I take each data set minus the mean of 4. And then I need to take the square of those distances. Now, some of you are going to go negative. You're going to take your blue calculator, for those of you who have these types, and you're going to say -3 squared. Now look how it's typed in. According to the order of operations, you do the exponent first and then the negative, and the calculator is going to do that correctly and give you -9. But that's not what we want. We want the entire quantity of -3 squared. All of your squared deviations from the mean must be non-negative. I'm going to say it again. All of these squared deviations from the mean must be non-negative. So I square that, I square -3 and I get 9. I square 0 and I get 0. So this is positive, it's non-negative. This is 0, it's non-negative. This is 9, it's non-negative. Then, according to my formula for population variance, I take each of those deviations from the mean, I square it, as I've done here, add them all up. So if I add those up, I get 18. And I divide by the population size. There are 3 data points in my population. So my variance for this data set is 6. This, if I'm telling you that this data set is the entire population of whatever it is we're measuring, then its variance is 6. Which is interesting because its range is 6 also. Now there is a slight difference if our data set is only a sample. Remember, if we're taking a sample, we find the sample mean, which is x bar. We take each of our data points and find the deviation from the mean, and we square that and we add them up, but we divide by 1 less than our sample size. Now there's a wonderful Khan Academy video that shows that. Ask me about it if you're interested, but for our purposes, it's not exceedingly important in our high school introductory statistics class, why we divide by little n minus 1 instead of big N for sample variance. What matters is that you know that if it's a sample variance, we divide by 1 less than the sample size. So I call this a kind of sort of average of the squared deviations from the mean. Now, what units does variance have? Well, let's say we're measuring things in terms of, I don't know, feet. X is measured in feet. The mean are measured in feet. So feet minus feet gives you feet. You square it, you get feet squared, you get square feet. And then a sample size or a sample size or population size or a sample size minus 1 just gives you, it's just a constant. So your variance would have a measure of square feet. Your data would be in feet and your variance would be in feet squared, or whatever units your data is in, your variance is in units squared. I don't even know what that means for, like, say we're doing dollars. What does dollars squared mean? I don't know. So variance can be confusing to some people. So in order for our measure of variation to have the same units as our data, we take the square root. So if we had feet squared, if our data were in feet, variance would be in feet squared. We take the square root of that number and we get feet. If whatever our units are, our variance will be in units squared. We take the square root of it and we get units. So if we have a population variance, we take the square root of that population variance, and we're going to call that a standard deviation. Just like variance, any given data set only has one standard dev. Now, if we use this formula, if our data set is a population, you'll notice this is the same formula for variance. We're just taking the square root of it to get the population standard dev. If our data set was a sample, we would take the sample variance, take the square root of it, and that would give us our sample standard dev. So a standard dev always has the same units that the data does. So in that first example I gave, the units were in, let's just say, feet. Our variance was 6 feet squared. So our standard dev would be root 6 feet. So we've just introduced two exceedingly important topics, variance and standard dev. Don't confuse variance and measures of variation. A measure of variation is the variance. Another measure of variation is a standard dev. So let's say I have data in a group, and I know this will freak you out when you see it, so let's just look at hat. So let's say that I have 3 1s, 3 2s, 4 3s, 2 4s, and a 5. To find the mean, I could go 1 plus 1 plus 1, because I have 3 1s. I got 3 2s, so that's 2 plus 2 plus 2. I keep going, and I get all of those means. And then I have 3, 6, 10, 12, 13 data points total. So I divide whatever that adds up to by 13. Then I can take each data point minus its mean, whatever this total mean is, and I can square it. Well, I've got a 1 3 times, so I have to do 1 minus x bar quantity squared 3 times. I have to do 2 minus x bar quantity squared 3 times because I have 3 of those. I have to do 3 minus x bar quantity squared 4 times because I have 4 of those, etc. So I'd add all those up and I'd divide by n minus 1. That would give me my sample variance. Then I would take the square root of that number and I would get my sample standard dev. Well, that seems pretty long, when we can easily see that the way to get the mean is to go, we already learned in our previous lesson how to find the mean. The sum of x times f, so I have 1 times 3, I'd have 2 times 3, I'd have 3 times 4, which is really what I'm doing in the numerator here, divided by the sum of all the frequencies, which is what I've got here. So I could use that formula for finding the mean of this frequency distribution. And then you'll notice I've done 1 minus the mean, and I can do that 3 times. So why not just do, if I'm looking at my, trying to create a simpler formula, my x sub I value minus x bar, square it, and multiply it by the frequency of that x sub I value. So I'm going to have 1 minus x bar quantity squared. Instead of adding it 3 times, why not just multiply it by 3? So once we know this formula for for variance and standard dev, then we can see that x bar is this from our previous lesson. And then rather than adding each of these separately and having 13 of these numbers to add together, why don't I just go my x data point minus x bar quantity squared and then multiply it by 3. And then I would take my 2 minus the mean, 2 minus the x bar, square that, and I'd multiply it by 3. Rather than just adding them up all the time, we're just taking advantage of the fact that multiplication is just repeated addition. So here's another formula we can use if our sample data, again, we know it's a sample because we have a lowercase s, a lowercase x bar, and we're dividing by n minus 1. All 3 of those tell us this is sample data. But if it's in a distribution, if it's grouped in a distribution, we can find the standard dev using this formula a little more simply than using the original formula. Now, if you have a calculator that you know how to use, I would ask you to enter in this data set, 1, 2, 3, 4, 5, 5, 5, 5, 5, 6, 7. Enter in that data set. And you'll notice the calculator, if you've done it right, will give you both values. It'll give you a sample standard dev and a population standard dev. What that means is if this data set is the entire population of things that we're looking at, then this is its standard dev, and this doesn't even exist. If, however, this is just a sample, a randomly chosen sample from a population, then this is its standard dev, and this one doesn't exist. To be honest, if it were up to me, after type and before you would if it were up to me, the calculator would not even tell you the standard dev unless you've told it, is this data set a sample or a population? If it's a sample, it would only give you this one, and if it's a population, it would only give you that one. And then, how do you find the variance? My TI-30X2S doesn't have a variance button, but it will tell us the standard dev. It'll tell us these. So how would we find the variance? We'd take these, whichever one is appropriate, and square it. The last thing in this video is the normal curve. Now, the normal curve is ubiquitous, actually. And here's what it looks like. For those of you who have taken calculus, you'll understand this about 10 seconds before everyone else. So let's draw a normal curve. So go ahead, draw your x-axis and draw your normal curve. Make it symmetrical. Make a ticky mark in the middle, right underneath the peak, and label that mean. Now, you don't just come out here somewhere and identify the mean plus one standard dev. I've identified it right here because this is the inflection point. You'll notice that between these two curves, or I'm sorry, between these two inflection points, the curve is concave down, it's opening downward. But once you get to this point and this point, the curve is concave up. Even though this keeps getting lower and lower and lower and approaching the x-axis here and here, it's still opening upward. So if you're just kind of freehanding this, then eyeball where your inflection points are. And those will mark your mean plus one standard dev, and this one over here is your mean minus one standard dev. So this distance between here and here is one standard dev. Go over that same amount again, and that's two standard devs. Go over that same amount again, and it will be three standard devs. Now, if your data are normally distributed, if your data form a normal curve, then the following is true. Within one standard dev of the mean, so we go from -1 to +1 standard dev from the mean, approximately, and this is just a rule of thumb, we'll use tables and get more accurate later, but approximately 68% of your data, if it's normally distributed, will fall within one standard deviation of the mean. 95% of your data will fall between -2 and +2 standard devs from the mean. So within two standard devs. And 99.7% of your data will fall within three standard devs of the mean. So from -3 standard devs to +3 standard devs. This is known as the empirical rule. Empirical means comes from measurement, and that's how we got this. Some people call it the 68, 95, 99.7 rule. Well, hey, if you can remember the name, you can remember the numbers, because there they are right in the name. So if your data are normally distributed, then whatever your mean and your standard dev of the data is, within one standard dev of that mean will be 68% of your data points. Within two standard devs of the mean will be 95% of your data points. Within three standard devs of the mean will be 99.7% of your data points. And of course, you go to four standard devs, you're somewhere 99.9 something, etc. Now, in theory, the normal curve goes on forever in both directions. So you never get 100% of the data points, but you know, that's kind of an extreme thing. We know there's not going to be any 20-foot tall humans, you know, way out here. And we know there's not going to be any negative 2-foot tall humans way out here. So we have to accommodate reality with our mathematical model. But for the vast majority of humans, let's say human adult males, the mean is here with a certain standard dev. And we could say approximately 68% of men are within this height to this height. Or women, the same thing, that just the mean would be somewhat lower. And even the standard dev, this distance, would be a little bit lower because the heights of adult women are not spread out as much as the heights of adult men are. But again, if our data are normal, 68, 95, 99.7. So that's all I have for you in this lesson, as if that's not enough, right? It's important to remember any data set only has one variance and one standard dev, which is the square root of that variance. And you get that variance by knowing which formula to use. If the data set is the entire population, use the population variance formula. If the data set is a sample, use the sample variance formula. And then whichever variance you use, take the square root of that, and you'll have your standard dev, which will have the same units as your data does. I think that's plenty for now. Have a great day.